Thank you. Good afternoon. My name is Gao. And that's the first slide. Back. Okay, I'm from R&D, Tata Steel Nederland, and just realized that I have prepared so many technical content, but missing a slide to introduce our industry. So we have more than 100 years producing very high quality steels, and we started from the Roya ovens. At the end of last century, we merged together with British Steel to form Chorus, and in 2007 we were taken over by Tata Steel until now. And our headquarters is in IJmuiden. We have about 10,000 people move there, and also we have so many downstreams all over Europe. And today I'm going to talk about welding simulations in steel production and applications. And this is the outline of my presentation. I will guide you through my talk via answering these 5 questions. Why welding simulation is important, which software package should be used, how to obtain reliable temperature-dependent material properties, how to create a reliable welding model, and what can a validated welding model do. And so the first question is why welding simulation is important, particularly for us as a steel making industry. After liquid steel is casted and hot rolled, welding is extensively used at our production line, namely a pickling line, cold mill, galvanizing line, and also packaging lines. Also, there are different types of welding processes involved, like flash butt welding, laser welding, arc welding, seam welding. However, I must say that the weld failures and also weld defects are inevitable, and the cause of these problems is generally not accessible from experiment. Therefore, it stimulates our research direction towards weld modeling. Here are 2 examples. So advanced high-strength steels are increasingly used by the automotive manufacturers because of the high strength and the good ductility. Therefore, the weight of a car body can be reduced. As a result, CO2 emission can also be reduced. However, increase in alloying content render these steels susceptible to welding problems, and hot cracking during laser welding is an example both reported from our production line and from our customers. And on the right-hand side, you see hot cracking in our production line. Well, it's a schematic picture of our production line that at the entry that we use laser weld the incoming coils with the previous coils in order to allow a continuous production. But from time to time, there will be failure of the weld. If you look at this image, your first impression would be maybe there is a misalignment, then it leads to a folding of the sheet. But if you zoom in the center, actually there is a centerline crack. And if we further zoom in at the location B, I have to say this is already a very lucky situation that the cracks is from the surface. But if you look at the location A, there is also a crack hidden in the weld, which could potentially be very risky in the subsequent processes like tempering or bending. And this is the second example from our customer. On the right hand side, you see an image. Hello? This is a very well-known body in white car frame. You see different colors, so different steel grades are used at different locations for different purposes, particularly for the pillars that we need high-strength steel to guarantee an impact resistance. But yeah, from our customer, they want to weld as close to the edge as possible. Therefore, they also observe this solidification crack. This is from Volvo. This video shows a hot cracking during laser welding, which is taken from a high-speed camera. I will tell you later on how we managed to make such a nice video to see the cracks during welding. But if we want to quantify the hot crack, that there is first of all a German standard that we prepare a rectangular sample. We clamp one side, we weld from the free edge with an inclined angle. After welding, we measure the length of the crack in order to rank the susceptibility to hot cracking for a material. This is a sample. There is another test called self-restraint test with taper shape. In this sample, then we don't need the external clamping. We just make a centerline welding, and then we measure the crack length. This is the sample. And currently, there are two indexes used in R&D Tata Steel to rank or to calculate the hot cracking susceptibility for a material. And then we can choose the welding parameters from the weld table accordingly. But if you look at the figure, that the two indexes doesn't match very well with the experimental measurement. The reason is also very simple, because in this equation there is only chemical composition. But the welding is a very dynamic process which involves local melting, high thermal gradient, uniform plastic deformation, residual stresses, microstructure evolution, and also segregation of the element. Therefore, a more meaningful hot cracking index should not only be based on the chemical composition, but also we need information from thickness that can be derived from the rolling process, microstructure from the heat treat process, coating from the galvanizing process, and also the local welding and joining condition. All this information is very difficult to obtain from an experiment. That's why we need the help from the model. Now we come to the second question: which software package should be used? Currently in R&D, we have many softwares that can be used for weld simulation, like MC Mark or Abacus. This is more like a general engineering platform. And Micros is used to model the microstructure evolution. It's based on phase field modeling. COMSO is a multi-physics and multi-skill platform. And Swantech Sorpas is a dedicated software for the resistance spot welding. And of course here we also have very close collaboration with Simufact welding forming. And we use Thermocalc and JMAT Pro to calculate the material properties. Speaking of welding simulation, it mainly consists of two parts. One is to obtain the temperature-dependent material properties, and the other one is to represent the physics during welding process. Now we first come to the first one. And here I show you how I obtain the temperature-dependent material properties of DEEP 800. Due to the confidential reasons that I deliberately hide the chemical composition, but you could see from the images in the middle that based on the chemical composition that we can calculate the thermal and the physical properties up to melting, namely thermal conductivity, specific heat, density, expansion coefficient. But for the mechanical properties, it's not only based on the chemical composition, but also it is determined by the subsequent heat treatment or what kind of phases is formed. Therefore, we have to compare with the high temperature tensile test to determine the material constant and also the hardening slope. And with that, we can obtain the flow curves at different temperatures. So now we are confident about the material property. Then we go to the question how to create a model. In this slide, I'm showing you an example for arc welding model. In the middle top image, you see this is actually the essential part to make a thermal model for arc welding, that you need to have proper heat generation, heat dissipation in the workpiece, and also heat loss, either from radiation, convection, or conduction. And on the left-hand side, you can see that actually within the arc, the physics is so complicated. You cannot fully represent all these forces in the arc. But luckily, there is a very smart guy called Gao. He proposed a double ellipsoid heat source with Gaussian distribution on the right-hand side to represent the heat flux internally distributed. And this is an example for the laser brazing, so we can also add some deposited material to glue the workpiece. And this is a resistance spot welding model that with this model, we don't really need artificial heat flux like arc welding or laser welding because the heat generation is based on the draw heating. So what we need is extra property. It's like the electrical properties for this material. Then we can also extend this spot welding model to a seam welding model. So basically this is a combination of rolling process together with the resistant welding process, but then the contact resistance is very dynamic. And in the end, that we also have the capability to conduct the phase field modeling to simulate the microstructure evolution during solidification. Now we have a good model, and I have to say that every model can give you a prediction, but whether the result is valid or not, you need to compare with the experiment, namely validation. So for the thermal part, that we use some thermocouples to measure the in-situ temperature during welding, and then after welding, we measure the location of the thermocouple. Then we extract the predicted time temperature profile at same locations. I have to say that I'm quite satisfied with this validation that not only the peak temperature, but also the temperature profile in the heating and the cooling stage are very good resemblance with the measurement. Now I talk about how to measure the strain during welding. Actually, from this image, you can see that there are two cameras placed there. But I think most of the people may think this is just a normal digital image correlation approach. Actually, it is not. Just imagine that if during laser welding, the laser plume is so bright, so basically these two cameras do not see anything. So our solution is to put a bandpass filter in front of these two cameras. You can see this is a typical plume wavelength of the laser plume, and then we have to select 450 to put a bandpass filter, which means that only the blue light will go into the camera. But this also introduces another problem, that only the light with this wavelength or within this full width half maximum will go to this camera. Therefore, we need to put two additional blue LED for the illumination purpose. With that, we can manage to measure the in-situ strain during welding, and we can also compare with the experiment with simulated results. And there are two images. One is far away from the weld, one is close to the fusion area. It's a very good validation with as function of time. And also we have chosen a time instance that laser is somewhere in the middle of the weld, that we compare the strain distribution. So basically we are satisfied with this validation. So now we have a validated model. The next question is, what can such a model do? I will give you 3 user cases. The first one is we use this validated model to calibrate the laser efficiency for different machines. Here's an example that in R&D that we have an ND-YAG laser. At our governance level 3, we have a CO2 laser. So if you look at the wavelength, it's already 10 times difference. I can guarantee you that even you use same power, same weld speed, the net heat input goes to the material will be very different because besides the wavelengths, there are also different factors influence the heat input, that is energy distribution, focal length, surface conduction, and keyhole mode. So we use our model to do the reverse engineering. Then we can calibrate the efficiency of different laser machines. So from now on, that any findings from R&D can directly translate to the production line based on the net heat input. The second example is about hot cracking. I have already introduced you just now that this is a standard test. We conduct some welding experiment, then we measure the length of the crack. Accordingly, we create the numerical models. And on top right-hand side, you can see we set the same welding speed, power, and you can also see that we use conical shape of the heat flux. But in the middle, that we have also define a bonding strength in the weld mushy zone. We start that here you can see with different weld strengths in the mushy zone that the material can have different responses during laser welding. Because this is the intrinsic properties of our product, I cannot share you the exact value, but I marked as criterion 1 to criterion 4. And there is a decreasing tendency of the strength. So if you see this model with criterion 1 and the weld is intact, with criterion 2 that you can see there is already an onset of a crack. With a criterion 3, you could see that the crack is initiated and also propagated. With criterion 4, that you can see this crack is propagated just after the weld tail. And on the right-hand side, you can see sample that when it's cooled down to room temperature, it's fully fractured. This is the sample with the criterion 4. Now we come back to this video again, that it makes more sense to see that we can very good represent this hot cracking during laser welding process. In addition, that to compare with the experimental measurement, that we compare the length of the crack, we determine that for this DP800, the intrinsic property for the weld strength in the weld mushy zone is with criterion 3. Then we come to the production mode, because in production we always have the butt welding configuration. So basically, you put the two coils together and then make a weld. In this model, I didn't include any criterion, so it's just a welding simulation. But in the next model, I've put the criterion 3 from DP800 to this model, and I was surprised that in our production model, that with this criterion, it didn't show any crack. I've chosen 4 time instances. The first one is when weld just started, and second one on the right-hand side is when the laser is a bit moved inside, but the starting edge is still molten. And the third image is the starting edge is cooled down to solid, and the fourth image is when the laser is moving further away into the sheet. So now I'm thinking that can we just model an extreme condition that with criterion 4, and can we enforce a crack? The answer is yes. If you could see from the image, from second and third and fourth image, there is a crack in the middle. And if after we enforce a crack, now the next question is, can we prevent this crack? Answer is also yes, we can come up with a solution. So even with this criterion 4, that we can reduce 10% of the power, then there will be less contraction after the weld pull. But in order to guarantee the same weld width and also the penetration, we have to preheat this sample to 300 degrees C. And we thought that we can still have an intact weld. So I think for the modeling, that it can give us not only the study for hot cracking, but it can also provide us much more insight of what is really happening during welding. So like the first image shows the temperature evolution, and the second image on the right hand side shows the effective plastic strain evolution, and third image shows the stress evolution during welding, and the fourth image shows the microstructure evolution. It's very accurate because in the weld, after solidification, we have the formation of martenset. And we can also, based on the welding model, to do some post-weld heat treatment simulation. And in the first image, you can see that we first translate the welding-induced result to this model. Then we also include the creeping effect. Therefore, the residual stress from the welding will transform into the creep strain. And for this, the second image shows the temperature evolution. Because our target temperature for the heat treatment is 500, so it won't involve any microstructure change. That is also proven on the third image. And for the fourth image, we can see that after the post-weld heat treatment, the stress is released and also more homogenized and redistributed. And yeah, here is also a case study that we compare with the post-weld tension for the sample with and without post-weld heat treatment. We could see that the sample after welding and also with the heat treatment has much lower residual stress and has also a much homogenized distribution of the residual stress. And all the models I talked about before, it's based on the finite element modeling. Here we also have a work on the phase field modeling. So we model the microstructure evolution during solidification. On the first row, you can see this is for a trip steel. We model at the tail of the weld pool how the liquid becomes solid. And if you compare the image C with image E, that's for a trip steel and a DP steel with the same solid fraction. And you could already observe that the trip steel has more secondary dendritic arms compared to DP steel. This will result in the image E, F, and G that there is more phosphorus segregation for the trip steel. And last image is stress distribution parallel to the welding direction, and plotted on the right hand side. You can see that for the trip steel, there's a higher stress gradient at the green boundaries compared to the DP steel. That makes the trip steel more susceptible for hot cracking. And all the models I just now talked about is all based on the numerical model, but there is also a model missing, that is analytical model. It's based on the big data or artificial intelligence. A lot of people think this could be the research future. Also, a lot of people think this could be high. Anyhow, that we also conduct a through process machine learning on weldability based on the advanced analytics. Here are some, actually this is the routine for different departments in Tata Steel, that we start from material design department, then we go to the rolling, heat treatment, galvanizing, and then we sell our product to the customer to do applications. It can be either welding or forming. So if we want to create artificial intelligence model, that we have to translate all these blocks with two input variables. So material design will determine the chemical composition. Rolling will determine the thickness. Heat treatment will determine the microstructure. Galvanizing will determine the coating type. And application in this case will only talk about welding. So if you want to create such a model based on the big data, these blocks is not anymore a sequential order, but they become parallel order. Then we have to translate these input variables to meaningful parameters, like chemical composition. You have each element. For the rolling process, you have the rolling force, and speed, interval, and for microstructure, there is temperature, time, cooling rate, and coating, there is type and surface, and for welding, there is also local welding situations. So we are not capable to create a model for now to include all the blocks, but to start with, we have picked all these blocks. Here is a model, and this is a universal model, so it doesn't matter if you change another material or if you change another welding process, because the input variables is based on the chemical composition, sheet thickness, and also the welding current. We set our target function is the tensile weld strength at the current maximum. And we have learned our data in past 10 years, and we split it into 70% of the training set, test set. We have chosen 4 models: a multilinear regression model, decision tree, random forest, and neural network. And from the regression model, actually you can get an empirical equation that your target function is on the left-hand side, and then you get all the input variables multiplied with a certain coefficient and plus a bias. And for the decision tree and the random forest model, that you can have the tree structured blocks. At every block that you make a judgment whether it's split into the true or false until you have the lost layers. And the advantage of have such a random forest or tree-like model is that you can know the weighting factors of all your input variables. For instance, to determine the final tensile strength, that carbon has a weighting factor of 0.3, which is the dominating factors. And the second weighting factor is thickness, followed by welding current, manganese, silicon, etc. So this is valuable information for our material design department to make the chemical composition or material recipe. And in the end, we also have a neural network model, but it's so complicated, not to go detail for this. Yeah, this is a technical presentation, so I don't have any conclusions. This is just a recap of my talk.